Looking at this graph, I'm going to focus now on a jump discontinuity. I will always have a jump discontinuity when I have a denominator that creates restrictions and it cannot be factorized away. In other words, I'm definitely going to have an asymptote. You can see that there's a vertical asymptote when x is going to be equal to 2. In other words, as I tend towards my graph from the left or from the right, I'm going to have to hop over that asymptote. In other words, there is a jump discontinuity in this case. Every single time I see a vertical asymptote, I will have a jump discontinuity. The other time where you could find a jump discontinuity is if you have a split graph and you find the limit as I tend towards a particular x value, in this case when x is 1, from the left and from the right, and you don't arrive at the same height. So over here, if I take a look, f at 1 is going to be equal to 0. What is the limit as x tends towards 1 from the left? Substituting into minus x minus 1, I'm going to get that I've got minus 2. Now finding the limit as x tends towards 1, but this time from the right, I must substitute into x squared plus 1. And here my limit comes to 2. As these two limits indicate that my graph arrives at different heights, there is a difference in the heights, which means that there is a jump between the heights. And so there is a jump discontinuity. The jump discontinuity is shown very clearly over here in this split graph. You can see that I have an increasing gradient straight line on the left of x is equal to minus 1, and I've got a horizontal line on the right of x is equal to minus 1. At x is equal to minus 1, my height is minus 1. So although the graph exists when x is minus 1, there is a difference in a height as it tends to minus 1 from the left, reaching a height of 2, or from the right, reaching a height of minus 1. In other words, here, showing it pictorially, you can see that there was a jump discontinuity exactly when x was equal to minus 1.